So here in this question, we have been asked that show that the determinant of a 2 cross 2 matrix sigma dot A is invariant under the given transformation, where sigma dot A goes to sigma dot A dash, which is equivalent to exponential I sigma dot n cap phi by 2 sigma dot A exponential minus I sigma dot n cap phi by 2, where the matrices sigma are the Pauli matrices. Find A dash k in terms of ak when n cap is in the positive z direction and interpret your result. Okay, so firstly you have to check that if the determinant under this transformation is invariant or not, and then we have to find A dash k in terms of ak, where n cap is only in the positive z direction, and we have to interpret our result. So to begin with, let us calculate sigma dot A. So it is just A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. Now we know that sigma 1, sigma 2 and sigma 3 are the Pauli matrices. If you don't know, sigma 1 is 0, 1, 1, 0. Sigma 2 is given by 0 minus I 0, and sigma 3 is given by 1, 0, 0 and minus 1. So from there we can calculate sigma dot A. We will get A3 A1 minus I A2. The third one we'll get here is A1 plus I A3, and here we'll get minus A3. So now let's calculate the determinant of this matrix. So determinant of sigma dot A is minus A3 square minus A1 plus IA3 times A1 minus IA2. This will give us minus of A1 square plus A3, sorry, this will be A2 square. Alright, so we can write this as minus of A1 square plus A2 square plus A3 square. So now this you can see it's just the magnitude squared of A. So we get that the determinant of sigma dot A is just the negative determinant of A squared. Now we'll check for the determinant of sigma dot A dash. Now sigma dot A dash is equivalent to the exponential of I sigma dot n cap phi by 2 sigma dot A exponential minus I sigma dot n cap phi by 2. Alright, so by the property of determinants, we know that if we have a determinant of some matrices x, y and z, we can calculate them like determinant of x first, then determinant of y, and then determinant of z. So that's what we'll do. But firstly, we have to find what exactly is this exponential term. What exactly does this exponential term give us? Because essentially it should be some matrix. So let's calculate that first. So we know that exponential of some variable x is given by like x to the power 0 0 factorial plus x to the power 1 1 factorial plus x to the power 2 2 factorial and so on, which can be condensed and written as, for some n goes to 0 to infinity, x to the power n by n factorial. So what do we get for exponential? Exponential of some plus minus I sigma dot n cap phi by 2. Let's write it in the condensed form. So we'll get some n goes to 0 to infinity for some plus minus I to the power n, then phi by 2 to to the power n, and then we'll get some sigma dot n cap to the power n by n factorial. So this is what we'll get. Now let's check for these values of sigma dot n cap to the power n. We'll check for the values of n for smaller values like 0, 1 and 2. Let's check them, what we'll get. So for sigma dot n cap to the power 0, we'll get 1. Yeah, that is pretty obvious. Let's see for sigma dot n to the power 1, we'll just get sigma dot n cap. Now let's check for sigma dot n to the power 2. So for sigma dot n cap square, we can write it as two sums, where for sum over I we can write it as ni sigma I, and for j we can write it as j nj sigma j. So now we can further write it like I comma j ni nj sigma I sigma j. Now from the property of polymatrices, we know that sigma I sigma j is Kronecker delta ij plus some identity matrix which is of the order of 2 cross 2 plus I Levi-Civita sigma k. So we will put this value over here. So let's try putting the values and try to expand this expression. So we have sigma dot n cap square, which is equal to summation of I comma j ni nj and Kronecker delta plus identity times identity plus I Levi-Civita sigma k. So now let's expand this. Let's see what do we get. We get I comma j ni nj Kronecker delta times identity plus sigma I comma j ni nj Kronecker delta ijk. I'll keep the iota outside and sigma k. All right. So let's see. Let's check for I is equal to j, because that is the only case we'll need, because the sigma here is identical. So sigma I will be equal to sigma j, and so we'll just put the index I is equal to j. So what happens here? In this case, we'll get ni square and Kronecker delta would become 1, and we'll get the identity matrix, plus we'll get here is, since I would be equal to j, so the Levi-Civita symbol would become 0. So this whole term would result in a 0. So we'll just get a 0 here. So from here, ni square, so ni square would be just 1. So this whole expression would give us identity. So we can check that we have a pattern here. So as I wrote earlier, this would give us 1. We'll consider that to be the identity matrix in matrix space. Then for power 1, we got sigma dot n cap. For the power 2, we are again getting an identity matrix. Now if we just multiply sigma dot n cap on both sides, we can see that we'll get this expression sigma dot n. So we can see a pattern repeating here for the even powers of sigma. So for say sigma dot n cap to the power 2n, it's always equal to identity, and for sigma dot n cap to the power 2n plus 1, it's always sigma dot n cap, where n runs from 0 to 1 to 2, 3 to infinity, all the way to infinity. So now for the exponential function that we got earlier, which was plus minus I 5 by 2 sigma dot n cap, we can expand it into two series. One would be for even powers of n, and one would be for odd powers of n. So it would look something like this. So we can write it as, for n goes to 0 to 2n, we get plus minus I to the power n 5 by 2 to the power n, and sigma dot n cap to the power n by n factorial, plus we'll get n goes to 1, n goes from 0 to 2n plus 1 for plus I n plus 5 by 2 n sigma dot n cap n by n factorial. Well, I think there's something wrong here in these two summations. So to simplify the notation, I'll just write these for even ends and these ones for odd ends. Alright, I guess that fixes the problem. So we can see that this series for even ends, it would look like 1 minus 1 by 2 factorial, 5 by 2 to the power 2 plus 1 by 4 factorial plus times 5 by 2 to the power 4, and all these terms would be just identity or 1. So here's the identity matrix that odd would all of them would be multiplied with, and for the next series it would be plus minus I 1 by 1 factorial 5 by 2 and minus plus I 1 by 3 factorial 5 by 2 to the power 3 and so on, times there would be a sigma dot n cap. So we can identify these two series. So this series here is just the series of cos, and this here is the series of sine with a multiplicative factor of plus minus I. So we can further write it as cos of 5 by 2 times identity matrix plus minus I sine 5 by 2 sigma dot n. So now it would be easy to calculate the determinant. So this expression here is nothing but the exponential of plus minus I sigma dot n cap 5 by 2, that is equal to this expression here. So let's try writing this in the matrix format. Let's see what do we get it in the matrix elements. So this here will give us just cos 5 by 2 0 0 and cos 5 by 2, and this here would result in plus minus I sine 5 by 2 times n3 plus minus I sine 5 by 2 n1 minus I n2. Here it would be I sine phi by 2 n1 plus I n2. This would be minus plus I sine phi by 2 n3. You can take a moment and try to absorb these results. So I would like you to pause the video and just verify the results here for a moment. After you're done with that, now let's just add these two components here, and we'll get the following matrix: cos phi by 2 plus minus I sine phi by 2 n3 plus minus sine, there's iota here, sine phi by 2 n1 minus I n2 plus minus I sine phi by 2 n1 plus I n2 and cos phi by 2 minus plus I sine phi by 2 times n3. Now we will calculate the determinant of this whole matrix, because that's the that's what we'll need to, like, we have to show the determinant is invariant under the transformation. So we'll just calculate the determinant of this whole matrix that we got. So what would be the determinant of this matrix? So let's calculate the determinant. So this times this, so it will give us cos square phi by 2 minus plus I cos phi by 2 sine phi by 2 n3 plus minus I cos phi by 2 sine phi by 2 n3 plus sine square phi by 2 n3 square, and this will just give us minus of minus, because the I square will give us a minus 1, and the plus plus minus minus will just give us a plus sign. So we'll get a minus sine square phi by 2, and here we'll get n1 square plus n2 square. Alright, so we can see that these two terms cancel out, right? And further we get cos square phi by 2, and this is a minus minus, so it will become plus. So we'll get plus sine square phi by 2 n1 square plus n2 square plus n3 square. Now this, since n cap is a unit vector, this whole expression is just its magnitude, which is 1. So we get cos square phi by 2 plus sine square phi by 2, which is again 1. So the determinant of iota plus minus sigma dot n cap phi by 2 is just 1. Hence we can show that determinant of sigma dot a is equal to determinant of sigma not sigma plus I sigma dot n cap phi by 2 times determinant of sigma dot a. I'm sorry, here there will be a dash because this is after the transformation, times determinant of negative I sigma dot n cap phi by 2. So these two values, this one will be 1 and this one will be 1. So we can see that the determinant here is invariant under the transformation. Alright, so the next part of the question asks us to find ak prime in terms of ak. So, and they have given the condition that n cap is in positive z direction. So we can take the n cap would be equal to 0 comma 0 comma n3, and since n cap is a unit vector, the magnitude of it should be 1, so we'll just take it 0 comma 0 comma 1. So now we put this value in the determinant expression that we found for the exponential. So here we can see that n1 and n2 are 0, so these values right here would become 0 and would give us just these two values over here. So let's write it down. We'll get cos 5i2 plus minus I sine 5 by 2 and 3 times 0, and here's a 0 2, and cos 5i2 minus plus sine 5 by 2 and 3. So we can write these two expressions as two exponential functions, because n3 is just 1, so we'll get this, and this n3 is also just 1. So as you can see, this here is an exponential, and this is here also an exponential, and this exponential will be just plus minus I 5 by 2, and this one would be minus plus I 5 by 2. I hope you get what we have done here. We have just used Euler's formula. So if you don't know, we can write e to the power I theta as cos theta plus I sine theta. That's what we have been using here. So we get this expression plus minus I sigma dot n cap 5 by 2 would be equal to e to the power plus minus I 5 by 2 0 0 into the power minus plus I 5 by 2. So this is the matrix that we get. Now we have to, in order to find a prime k terms in terms of ak, we'll just use the transformation rule that we have been provided with previously. So we know that sigma dot a prime is equal to the transformation e to the power plus I 5 by 2 0 0 e to the power minus I 5 by 2 times the sigma dot a times e to the power minus I 5 by 2 0 0 e to the power plus I 5 by 2. Now again, from previous results we know that what is the expression of this term. This term is just a3 prime a, let me just see it once. Right, so a3 a1 minus ia2, so this will be a3 prime a1 minus ia2 prime a1 prime plus ia2 prime, and this will be a3 prime negative. Right, so we get this expression here, I 5 by 2 0 0 e to the power minus I 5 by 2. Similar expression, just no primes, a1 minus ia2 a1 plus ia2 minus a3, and e to the power minus I 5 by 2 0 0 e to the power plus I 5 by 2. Right, so now we'll multiply this matrix. these two matrices first, then these two. So the first multiplication will fetch us a3 e to the power I5 by 2 times a1 minus ia2 e to the power I5 by 2, and here we'll get a1 plus ia2 e to the power minus I5 by 2, and here we'll get minus a3 e to the power minus I5 by 2. Just check if I have done it correctly. I think it's correct. Yeah, I think it's correct. And here we have this matrix still, e to the power minus I5 by 2, 0, 0, e to the power plus I5 by 2. Alright, so we further multiply this matrix. So let's see what do we get. So here we'll get a3 back. Here we will get a1 minus ia2 e to the power I5, because 5 by 2 plus 5 by 2, so it will be e to the power I5. No, yes, that will be e to the power I5. Here this element would be a1 plus ia2 e to the power minus I5. Yep, and this will be minus a3. This is equal to a3 prime, a1 prime minus ia2 prime, a1 prime plus ia2 prime, and minus a3 prime. So we can see that a3 prime is just equal to a3, a1 prime minus ia2 prime is equal to a1 minus ia2 e to the power I5, and a1 prime plus ia2 prime is just a1 plus ia2 e to the power minus I5, right? So we can first add these two equations and then subtract these two equations. So let's try adding them first. So let's call this equation 1 and this equation 2. So we'll add equation 1 plus 2. We'll get, if we add them, so we'll get 2ai prime, which is equal to a1 plus e to the power I5 plus e to the power minus I5 minus ia2 e to the power I5 minus e to the power minus I5. So you can see that here we'll get 2 cos phi, and again we'll get minus a2 2i sin phi. In case you don't understand this, just know that cos phi can be written as, in terms of the exponential functions, e to the power I5 plus e to the power minus I5 by 2, and sin phi can be written as e to the power I5 minus e to the power I5 by 2i. That's what we have done. We have just put these values here. So we get that a1 prime is equal to a1 cos phi minus I. Actually, this minus and this I and this I will become I square, so it will become minus 1, and this will become plus 1. So it will become plus a2 sin phi. Now let's see what happens when we subtract it. So we subtract equation 2 from 1, so we get, no, we subtract equation 1 from 2. So 1 minus 2, we'll get minus 2a minus 2a2 prime, which would be equal to a1 e to the power I5 minus e to the power minus I5, and minus ia2 e to the power I5 plus e to the power minus I5. Again we get, here we get two values of sine and cos, but there will be a I here, I'm sorry. So we have minus I to a2 prime equals to a1 to I sine phi minus I a2 to cos phi. So we get a2 prime equal to a2 cos phi minus a1 sin phi. So let's write all the results that we got for these a1 primes, a2 primes and a3 primes. So seems there was a technical issue, but it's all right, I guess. So we have a1 prime is equal to a1 cos phi plus a2 sin phi, and we have a2 prime is equal to minus a1 sin phi plus a2 cos phi, and we have a3 prime equal to a3. So we can write this whole thing in matrix notation. So we can write a1 prime, a2 prime and a3 prime equal to cos phi sin phi 0 minus sin phi cos phi 0, and these three terms would be 0 again. And here we have a1, a2 and a3. So you can recognize this from your classical mechanics course that this is nothing but a rotation about the positive z-axis. So this is our interpretation of the transformation.